Okay, welcome back. In this video, we're going to continue on talking about the book. We're going to look at the scalar circle, and we're going to compare that to the Euclidean circle and discuss how these are different. So this is going to be very important in understanding the the coordinate system that we're using with the 363 code, or 363 degrees. So I'm going to kind of walk you through that and help you understand that a little more clearly. So let's go ahead and get started. I'm going to share my screen and we'll get into looking at this. So let's do that. Okay. All right. So we're going to look at the 363 scalar circle, and we're going to compare that to the Euclidean circle. So when we do this, we'll go through and look at some of the salient differences between these two, and try to make it clear to you why we're using 363 degrees. So for really over at least 2,000 years, we've been taught that the circle is 360 degrees. But what if that assumption is incomplete? What if the circle was used for measurements is 360 degrees, but the circle that's actually models resonance and cyclic systems is actually 363 degrees? So let's try to look at the comparison. Now, I made this particular table so that we can kind of do a quick comparison between the differences. So I'm going to refer to the Euclidean circle as our kind of traditional circle at 360 degrees. And then our scalar circle will be, this is in reference to using a 363 degree coordinate system. So when we look at the Euclidean circle, we have more of a linear segmentation as opposed to a harmonic lattice. So in a scalar circle, we're actually going to be seeing that we can take the scalar circle and divide it into 11 intervals. So this is our primary system, and each interval being 33 degrees. I will show you a schematic of that if you're not familiar with that. Also, when we talk about constants that are used with these two different circles, in the Euclidean circle, like pi is used a lot in the Euclidean circle. Of course, pi is an irrational number. So rational numbers are defined as numbers that they don't repeat, and they just go on to infinity. The last digit there's never a repeat in the number. So pi is an example of one of these. And so is, if you look at the Fibonacci spiral, you will see that it's also an example of using a spiral that has exponential growth, and it assumes infinite recursion, which is not what nature's actually doing. It actually terminates. So then also in our scalar circle, we are going to be using rational numbers, rational ratios. You're going to see in the etheric lattice, you're going to see the numbers 3, 6, 9 appear as digital roots in this lattice. And I'm going to refer to this as a 1089 system because we will have numerical values that show up that are multiples of 1089. And this has geometric implications as well as energetic implications. I see the Euclidean circle as being more static and the scalar circle as being more toroidal and one that breathes. The primary function of the Euclidean circle is measurement, 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 measurement. And this particular system, if you look at it, is the 360 degree system is divisible by, you can basically break it into any increment that you desire. It's divisible by 1, divisible by 2, 3, 4, 5, 6, 8, 9, 10, and 12. This means that you can break it into increments of 15 degrees, say, or 30-degree increments, or 45-degree increments. Historically, the Euclidean circle was used a lot in astrology, astronomy, timekeeping, but it's really a mathematical model that you see for measurement. That's what you normally see. In Euclidean, if you look at segmentation, they're using it as increments of space. So you can pick any size that you like in the Euclidean circle, and you can think of it much like a ruler. When we look at more of the scalar circle, it's all about resonance, memory, and about cyclic flow. And the geometry types is more flat and abstract for Euclidean circle. And over here, we're going to talk more about, like I mentioned, energetic structure and flow. So in this model, if we look at this, the additional 3 degrees that we have from 360 to 363 degrees can be interpreted as more of a return phase that completes a full cycle of expansion and return. So as you look at these extra 3 degrees, what they represent, it's really the return wave, which I've characterized this as the dielectric, the inward breath that allows the system to fold, store memory, and remain coherent. So this is, if you're wondering where that 3 degrees, additional 3 degrees, what that means. So we can go back and forth between Euclidean and the scalar geometry or circle by this mathematical equation here. So if you take 363 degrees divided by 360, the conversion is 1.008 and then 33333. So as an example, if you were looking at the internal angle of an equilateral triangle that happened to be 60 degrees, then if you multiply it by this conversion factor, you will convert this to 60.5, which is the internal angle of an equilateral triangle in the scalar circle, in that system, that coordinate system. So I'll be talking about this conversion as we go through when we look at the different geometries. So really, if we want to understand magnetism, consciousness, and DNA geometry, and the architecture of the ether, we may benefit from expanding from a 360-degree world of measurement into a 363-degree universe of resonance. So let's first look at Euclidean geometry with like the 360-degree circle. We know the triangle is the most stable polygon. So polygons are classified as being, the mathematicians say they're 2D objects. So they're planes, and they declare these planes don't have thickness, and so they're 2D objects. They're closed in the fact that they have the ability to be closed figures or structures. And we can see that each vertex will exactly, will have 2 sides. So if we put a little point, if you were drawing it, would be known as a vertex. That's kind of the vertex is the word that's the more technical, but you can see we have 2 edges here, 2 lines, and they're connected here. So we have 2 sides here. This is another vertex, 2 sides. This is an equilateral triangle here. The internal angles here in the Euclidean geometry are 60 degrees. So this equilateral triangle is a total of 180 degrees. So this is the internal angles. So we like to measure internal angles. It gives us an idea of like If this had thickness, it would be more of the volume, if we're looking at like a tetrahedron, of the actual structure. You can also look at the digital roots and smash this down to a single digit. In 18 here in the 0, this would be 9. So if you were to put this into a three-dimensional structure, actually a tetrahedron's 4 dimensions, but if you were to put these into the well-known Platonic solids, which are where you take the polygons and you assemble polygons into a 3D structure, if the polygons are all the same, then you can get Platonic solids. So the tetrahedron is 4 triangles that are put together. The cube, which is a hexahedron, would be 6, taking 6 squares and putting them together. So the internal angles for a square, you can see here, 90 degrees. So this overall is 360 degrees. And then this is it's a 5-pointed structure. So this is the pentagon. Internal angles here for these are, for the pentagon are, it says 180 degrees here. And so this actually comes out to be, these should actually be 108 degrees. So this should be 108. And so this turns out to be a total of 540 degrees, also digital root 9. This is a hexagon. Internal angles are 120 degrees times 6. So this is 720 degrees. Here is if you look at this one here, this is the heptagon. So the internal angles here are 128.6. So this has actually been rounded because it's actually a 6-digit repeat number. And over here, this is the octagon, and the internal angles are 135 degrees. There are 8 of them, so it's 1080. So this here for the heptagon is 900 degrees. So you're seeing these represented, these polygons represented as represented as their internal angles, and this is all Euclidean geometry. So we can multiply these numbers if we go back by 1.00833333, and we can make the conversion into the scalar geometry. So that's what's happening here. If you, for example, take 90 times that conversion, 1.0083333, you'll get 90.75 as an internal angle for the square, 60.5 for the triangle. The pentagon is 108.9, hexagon is 121 for these internal angles. Here's the heptagon, 129.6, then 42857, and then here's the octagon at 136.125. And of course, then you can, because there's 3 sides, 3 angles, you can multiply this one by 3, this one by 4, this one by 5, this one by 6, and then you'll get these corresponding internal angles. And you can see that they are phase shifted relative to the Euclidean geometry. And then we can also look at the digital roots of these, and you'll see they're going to follow the 3, 6, 9. Okay, so then now we can continue, and this is just another slide looking at if you take the regular you take the polygons and put them together into 3-dimensional structures, then these are referred to as polyhedra, so a bunch of polygons being put together. And you basically see the same thing I was just talking about. I'm giving you the total angles, the summation of the internal angles here for these. And just as a note, the tetrahedron is referred to as fire. The octahedron air, the cube earth, the icosahedron water, and then the 5th element is the ether, which is the pentagonal dodecahedron. So you are wondering what these structures look like. This here is the tetrahedron, traditional tetrahedron with 4 triangles. This is the octahedron. It has, if you look, it has six vertices, but 8 triangular faces. This is the square-based pyramid. You can see It has a square on the bottom and then four triangles here. This is not a platonic solid. It's a Johnson, what's called a Johnson solid. Here's the cube over here, because what you have to have if you have a platonic solid is the polygons all have to be the same. And you can see the edge lengths are all the same here. And so you see here that you have the cube or the hexahedron. This over here, these are all triangles. So this is icosahedron. So there's 20 triangles in this structure here. And you can see they're all like connecting at this center point. There's three faces here. There's four faces here on the octahedron and so forth. So connecting to each vertex. Down here, so this is the rhombic dodecahedron. So you can see it looks a little bit different than over here. This is the traditional pentagonal, because you can see the pentagons, dodecahedron. This is a Catalan, classified as a Catalan structure shape. But the rest of these that are here, this one, this one, this one, this one, these five are the platonic solids. They're not really solids, but they are classified, and that's the nomenclature. Okay, so let's compare the Euclidean geometry with the scalar geometry. If we take and we use 1080, which is, this is the square base pyramid here. So if you look at Euclidean geometry, there's 360 degrees in the square. So each corner is 90 degrees. So 90 times 4 is 360 degrees. And then each triangle is 180 degrees. So there's four of those. So 180 times 4 is 720 plus the 360 gives you 1080. So that's what you would see like in ancient Egypt with the pyramid. What's sticking above the ground is this pyramid structure right here. So that one's very important. It's 1080. And then if you double that, you get 2160. And then this is times 3, times 4, times 5, times 6, times 7, times 8, times 9, times 10. And these structures, the 2160 actually is the cube. Some of these structures are known if you convert them into the platonic solids, or you can convert them into the Catalan structures. So if you look here, for example, 4320, this is going to be this is the rhombic dodecahedron. 6480 is the pentagonal dodecahedron. And some of these we don't really know. We don't have classifications for them, but they are multiples of like 1080. Now, I want you to take a look. If we do these conversions into the scalar geometry, remember we're going to multiply by 1.0083333, and you get this whole family of the 1089 multiples all the way down. So these are 1089 times 1, times 2, times 3, times 4, and so forth. The interesting thing is you take the difference between these numbers, you get the 9 times table. So that's very interesting because the number 9 has a much significance when we digital root it in our energetic system. It's on the hourglass of going in and out for the constriction point. Okay, so here's our 33 scalar lattice that I have been presenting. So now if we want to look at kind of why this is considered to be a kind of a phase lattice, is because we have the circle here. I've drawn the first inner circle. I have 3 concentric circles here. I'm going to focus on the inner circle. There are 11 in this example. There are 11 intervals that are broken into 33 degrees. So we have 11 times 33, or that's 363 degrees. So this is the lattice. It's the primary structure of the lattice. You can see we go from 33 to 66 to 99 to 132 to 165. to 198, 231, 264, 297, 330, and back to 363. So all these nodes here are like 33 times n. They're all multiples of 33. So every integer that you're seeing here is a multiple of the same kind of base, and that base is 33. So that's the interval. So this is we're dealing here with the model, or our interpretation here is a cyclic. These are cyclic representations, and it's we're seeing that the numbers we're dealing with something that's cyclic and repeating. The numbers have like relationships one between the other. You can see this is a doubling, so it's harmonic, like what you'd see in like music with octaves. But this is definitely, it's not pick any, increment you want. This is kind of like, this is set. It's a set increment that we're using. And we also will see like there's complementarity here with some of the nodes. So 66 is complementary with 297 to form 363. So we have opposing points that demonstrate complementarity. So you can think of these nodes here as like notes on a musical scale, but it's understood this whole system is cyclic and dynamic. It's repeating and it's an oscillating process. And this is where we get a little bit different than the 360-degree circle. So again, this is the scalar circle. And then if you want to go to the second concentric ring, you pick up here, 363 goes to 396. So this is another 33, and then you just continue to go around in this second concentric ring. And then you go and you do the same thing for the third concentric ring. So by the time each one of these is 11 intervals, so this one then would finish 22, and this one would be 33. And 33 times 33 is 1089. So if you notice on this radial here, there's important values. This is the scalar circle at 363 degrees if we go around one time. And then this is 726. This is actually the tetrahedron, and 1089 is the square base tetrahedron on this specific lattice. Okay, so now there is something else I'm introducing. I'm very excited to introduce this too, is that we can make a secondary lattice that's what I will call 11 lattice. And so we still have the 363-degree circle, but before I was just showing you 33, 66, 99, 132, 165, but we can make this a triad, and we can make it 11 degrees and 22 degrees and then 33 degrees. So I'm going to call this 11 lattice. Now, instead of having 11 intervals, we have 33 intervals, each one being 11 degrees. So this is the kind of the scalar. We like talk about this in the book as well. You can easily drop a triangle on here. So a triangle, you take 363 degrees and divide it by 3 because it has 3 vertices. You'll get where it's 121 degrees. So each arc here is 121 degrees. So we can place the vertices here. This is 121 degrees, or 11 times 11. This would be 242 degrees. And you can see the vertices of the triangle are locking into the actual nodes that are on the 363-degree scalar circle. So it's got, a triadic rotation that's aligned to the 11 lattice. So I'm going to talk more about that. This is kind of like a teaser, because I'm going to show you how the heptagon can fit on here, and I'm going to map back all those 1089 multiples, which are representing different dimensional shells in our system. And so here, to wrap up the video, 363 is not just a different number. It's a different way of modeling cyclic systems, one that includes both expansion and return. And this is what makes it so exciting because this is associated with looking at resonance and the universe is doing cyclic events. The universe is not doing linear events where you start in with a line you go to infinity. Everything that we see is cyclic. There's a return going on, and this system here that we're looking at is built to deal with that. Okay, so make sure that you tell everybody, your friends and everyone, to subscribe to the channel. I'm going to continue to add components that tie into the book to make the 363 code easier for you to understand. We can strike up conversations about that. If you have any questions about anything, just drop it in the email and I'll try to get to it. All right. I'll talk to you next time.